Welcome to Fourier transform infrared spectroscopy. For visible and ultraviolet spectroscopy, a photodiode array, or CCD, can be used to measure an entire spectrum at once. And in the IR region, we measure an entire spectrum using Fourier transform spectroscopy. So in Fourier analysis, a curve is decomposed into a series of sine and cosine terms. So let's look at an example. Note that here the curve spans from x1 equals 0 to x2 equals 10. So we've got our curve spanning from 0 to 10 here. And we've got some curve. Our Fourier series has the form that looks like this. We've got y equals a0 times sine of 0 omega x plus b0 times cosine 0 omega x plus a1 times sine 1 omega x plus b1 cosine 1 omega x plus a2 sine 2 omega x plus b2 cosine 2 omega x, and so on as we go up in integer. And that means that now we can then write a sum from n equals 0 up to infinity of a n sine n omega x plus bn cosine n omega x, where omega then is equal to 2 pi over x2 minus x1, which in this case is 2 pi over 10 minus 0, which is pi over 5. So note that this equation says that the curve can be expressed as the sum of an infinite number of sine and cosine waves, and each successive term corresponds to a wave with increasing frequency. So each additional term then is improving the fit of our Fourier series to our experimental curve. So we start out here with just n equals 0, 1, and 2. Then we get a fairly poor curve fit where we have just a single peak there. If we go down here to n equals 0 through 4, then we get this curve, and you can see we've got now 2 major peaks, but we also have this peak and that peak there that we really need to get rid of. And so if we increase from n equals 4 to n equals 0 through 8, then we get a much better curve fit, but we're still not perfect. We're still not exactly describing our curve here. And so if we continue to add additional terms, then we'll get closer and closer to our fit. And the Fourier analysis says that we're going to need an infinite number to compose our curve here. So this brings us to interferometry. The key to Fourier transform infrared spectroscopy is the interferometer, which we've shown here. So light from our source is coming and hitting a beam splitter here. The beam splitter is going that way, which transmits some of our light, and it's reflecting some of our light. So some of that light is being transmitted through this direction. Some of that light is going to be reflected that direction. Now, to simplify our explanation here, let's examine a case of monochromatic light. So in reality, a broad spectrum light source is going to be used, not a monochromatic one. Let's also assume that the beam splitter transmits half the light and reflects half the light. So when light hits the beam splitter at point O here, then some is reflected to our stationary mirror up there at a distance of OS. The other half is then transmitted to our movable mirror, that's over here, at some distance OM. And these rays are then reflected by our mirrors and returned back to our beam splitter. So the ray that went up here is being reflected back, and the ray that went this way is also being reflected back. And again, half of each ray is going to be reflected and half is transmitted. So one ray from each mirror goes back to the source. So this is the light that was reflected off the beam splitter, reflected off our stationary mirror, and comes back to the beam splitter. Half of that light gets reflected back to our source. The other half gets transmitted through to our detector. The other ray that can go back to the source has come from the source, been transmitted through the beam splitter, hits our movable mirror, goes back, and is then transmitted back through the beam splitter to the source again. The other half of that light coming back from our movable mirror is going to be reflected off the beam splitter and go to our detector. So again, the other way of light goes to our sample, and then to our detector, and light transmitted through the sample then strikes our detector. So our two optical paths, OS and ON, are not usually equal. So the two waves are not going to be in phase once they get combined again after the beam splitter. And this means that they're going to constructively and destructively interfere. So constructive interference will occur if they are in phase with one another, and destructive interference will occur if they are out of phase by half lambda, half the wavelength, in which case they will completely cancel. So we'll have an alternating intensity between constructive interference and destructive interference. Now if they're out of phase by any other amount, then they're going to partially cancel and we'll get some intensity of light in between those two values. The difference in path length delta is given here, where we have twice the difference in distance between OM and OS. And this difference is called the retardation. So if delta is an integer multiple of lambda, then the interference is constructive. So if we're at delta equals 0, or delta equals lambda, or delta equals 2 lambda, then we've got constructive interference. And if delta is a half integer multiple of lambda, then the interference is completely destructive. So if we have delta equals lambda over 2, we have destructive interference. If we have delta equals 3 over 2 times lambda, we have destructive interference, completely destructive interference. And if delta is anything else, then the interference is partially destructive. So we've got some value in between our maximum or minimum. So a graph of output light intensity versus delta is called an interferogram. And if the light is monochromatic, then the interferogram is a cosine wave. So the intensity of light I as a function of delta, or retardation, is equal to B, which is a function of wave number of our light, times cosine of 2 pi delta over lambda. And this is equal to B cosine 2 pi times the wave number times delta. So the intensity I is then a function of our retardation. And our B there is a constant that accounts for the light source intensity, the beam splitter efficiency, that is, it won't split our light exactly 50-50, and the detector response. And note that all of these are wave number dependent. So let's look at some interferograms. Here we have the interferogram here, and the spectrum of monochromatic light. So we have a single wavelength of light here at wave number of 2, and we have a nice cosine wave over here. And here we have dichromatic light, so 2 wavelengths of light. We've got our wavelength of light there at wave number 2. We've got our other frequency of light here at wave number 8. And now you can see that we've got 2 cosine waves. We've got one lower frequency cosine wave, and then another higher frequency cosine wave superimposed on that one. So here we have one peak with a non-zero line width. You can see we've got some finite line width there that isn't 0. And then over here in the interferogram, you can see we've got an oscillating interferogram, but it's trending to 0 at higher retardations. Here we have 2 peaks with non-zero line widths and 2 different intensities, and so you can see now we've got our interferogram again oscillating back and forth, trending towards 0. But also now you can see we've got 2 waves with different frequencies superimposed there. So the spectrum is the Fourier transform of our interferogram. That is, Fourier analysis of our interferogram gives us our spectrum. So in a Fourier transform spectrometer then, the sample absorbs some of the radiation exiting the interferometer, and that means that our interferogram contains the spectrum of the source minus the spectrum of our sample. So first, an interferogram of a reference blank, this is a cell in solid, has to be recorded, and this interferogram is then transformed into a spectrum. And then an interferogram of our sample is recorded, and this interferogram is also transformed into a spectrum. And note here that our interferogram looks significantly noisier than it did before, and that's because now we have something in there aside from just solvent. And now at each wavelength, the intensity from the sample is divided by the intensity from our blank to give us a transmittance, or percent transmittance in this case. And so you can see now we've got some absorption here at these bands, which now have low percent transmittance. And so the resolution of our spectrum is approximately 1 over delta per centimeter, where delta is the maximum retardation. And note that the maximum retardation is double the maximum mirror travel, because the light has to travel that distance twice, once on the way to the mirror and once on the way back from the mirror to the beam splitter. So if the maximum mirror travel is plus and minus 2 centimeters, then the resolution is 1 over 4 centimeters, which is 0.25 wave number. So the wave number range of the spectrum depends on how the interferogram is sampled. If you want a range of delta nu wave numbers, then you need to sample the interferogram at retardation intervals of 1 over 2 delta nu. For example, if you want a range of 4,000 wave numbers, then you must sample at intervals of 1.25 microns. So note that this sampling interval corresponds to a mirror motion interval of 0.625 microns, because again, that light has to travel that distance twice. So if the mirror moves at 2 millimeters per second, then the data collection rate is 3,200 points per second. So compared to dispersive spectrometers, a Fourier transform spectrometer offers us better signal-to-noise ratio at a given resolution, better frequency accuracy, faster acquisition time, built-in data handling capabilities because there is already a computer attached to perform our Fourier analysis. And our signal-to-noise improvement here is arising mostly because our Fourier transform spectrometer uses energy from the entire spectrum instead of just a small amount of monochromatic energy. Furthermore, multiple scans can be averaged due to the high reproducibility of wave number position, and this precision and low noise allows minute changes in the spectrum to be observed by subtracting one spectrum from another. But Fourier transform instruments are not as accurate at measuring transmittance. FTIR instruments are essentially so common that there are no commercial dispersive infrared instruments. But for ultraviolet and visible spectroscopy, the mirror motion is too small to control, and that means that Fourier transform instruments are not feasible. So that was Fourier transform infrared spectroscopy.